Hello everyone, welcome to the manufacturing processes class. In today's video we're gonna practice on the riser design, sprue design and the Buoyancy force. We have covered this like over 2 videos before. We have discussed the Buoyancy forces and their effects on or the pushing that comes from the molten metal in the mold cavity on the coop and how we can take precautions against the Buoyancy force. So today we're gonna solve some examples over the calculation of the Buoyancy force and how much of the weight that should be added to avoid the displacement or the moving moving the cube with respect to the jack because of the Buoyancy force. Also, we have discussed the down sprue design and the relation between the area at the top of the down sprue to the bottom area of the down sprue. And also we discussed the different three methods of the riser design, and we said that we're gonna focus on we're gonna use two methods, two of them which are the Nevada Research Lab method in addition to the Chevernov's method. So today in this video, first I'm gonna go over the different laws and formula that we have discussed before, and then we're gonna solve some examples that already provided to you through exercise sheet number 4. So this is like a summary of the different formula that we're gonna use for solving this sheet. Starting with the molten metal flue in down sprue. We said that this is a typical shape of a down sprue, that you're gonna have the thing on the top here. This should be the boring cup, and the stable shape, it should be the down sprue. And we said that it should be tapered to avoid the aspiration, and that's why it will have two different areas. There is an area on the top and area at the bottom of the down sprue. And VTVB, this stands for the velocity of the molten metal at this area on the top and this area or at this level and the bottom, assuming that the velocity of the molten metal at the tip of the boring copper is already 0. So that's why we're going to consider this is like a datum. And HT, this should stands for the the boring cup height, and HB, this stands for the total height of the down sprue, including the plus the boring cup height, which in many of the cases we're going to consider this at the coop height as we explained before, right? Just an approximation, neglecting the thickness or the effect of the down of the spool, because in many of the cases the spool will be located in the jack. It means that we could say that here we're assuming that this is the parting surface, and all of this is just belong to the coop. So in this case, we're gonna have this HB, it will be equal to the HC, where C stands for the coop height, right? So there are some fundamental formulas or equations here that govern the flow of the molten metal inside the down sprue, that this fluid should be a laminar flow with no turbulent flow to avoid the trapping air and bringing air inside the mold cavity. So we said that the Q, which stands for the volume flow rate of the molten metal inside the down sprue, should be equal to the area times the velocity. This is what we knew from the fluid mechanics, which is going to be the area at the top time the velocity of the molten metal at the top area equal the area at the bottom time the velocity of the molten metal at the bottom area of the down sprue. In the meanwhile, we have driven using the Bernoulli equation. The velocity at the top, it should equal to the square root of 2g ht, where ht again stands for the height of the boring cup and g stands for the gravitational acceleration. If we decided to work with the centimeters, so we're gonna substitute for g in terms of g will be, in this case we're just gonna plug g here, 981, and this will be in terms of centimeter as a height. So we're gonna end up with this velocity as centimeter over second. The same thing applies for the second velocity at the bottom. It means that we're gonna consider a different height from the datum, which is HB, and we said that HB in many of the cases is gonna be the coop height. And if we plug these three equations together and we solve them together and we did some manipulations, we're gonna end up with this ratio between the area of the bottom and the top area of the down sprue. It's gonna be the square root of HT over HB, where HT again, this is the coop height, which is gonna be like in 50 and 100. There are some standard values. I told you in case that I didn't give you HT, you're gonna consider it by 50 millimeter in case that it is not given. So this is for what we discussed about the down sprue design. Then we discuss also the Buoyancy force. The buoyancy force, this is the pushing that comes from the molten metal acting on the cube at the parting surface. So the buoyancy force, we express this one in as rho mgha, where rho stands for the density of the molten metal. So rho here, this stands for the molten metal density or metal density, which is going to be given density, which is going to be given, as we mentioned, that this is going to be like 7.8 gram per centimeter cube for the case of steel, for example. So it means that it is already commonly known for the density for some materials. Anyway, it will be provided to you. G, this is the gravitational acceleration. H, this stands, we said that this is the height of the this is like the height of the related to the height of the molten metal inside the mold cavity, and in addition to the sand. So we said that this parameter all the time we're going to consider as the cube height, in addition to the area, which is the projected area of the molten metal. What is the projected area? As we discussed, if you try to look to the shape from the top, you're going to see like a projection of the casting or the mold cavity. Actually, it should be the mold cavity, the projected area of the mold cavity, and I'm going to show you when we solve some examples how we can calculate this projected area with more details. But this formula here, it's going to be considered in case that we don't have any core, and in addition the casting is completely located in the drag. And this is basically what we do. In case that there is no core, in many of the cases the casting will be completely located in the drag. In some more complex shapes, some portions of the casting would be located in the cube, and the larger part or portion should be located in the drag, as we discussed before. But in many cases we try to bring the or just locate the casting completely to be located in the drag. But if for some reason if the pattern will break the sand, so in this case we may have portion of the casting would be located in the cube. So but this formula, which is rho mgha, this is going to be used in case that there is no core and the casting is completely located in the drag. But how about if there is a portion of the casting, a part of the casting that is going to be located in the cube? So this portion, the weight of the casting that is going to be located in the cube, it should be subtracted from the buoyancy force, because this term, which is rho gha, this is in case that we're assuming that this is the pushing comes from the molten metal, assuming that it is completely located in the drag. But if there is a portion of the casting that is going to be located in the cube on the top, it means that this weight of this portion of the casting, it will work against the buoyancy force. So that's why it should be subtracted here. Like the total force that needed or as a push over the sand, over the cube, it will be the difference between this term negative, the portion or the weight of the portion or the part of the casting inside the core, inside the cube. Make sense? How about in case that we have core? So in these two cases, we're going to use these two formulas in general in case that there is no core. But if there is a core, there is an additional pushing comes because of the pushing acting on the core. Like the molten metal is going to push the core, and then the core is going to push the cube. So there is like indirect effect from the molten metal. Like there is again, like we do have two parts, you could say, of the buoyancy force. One part which comes through pushing as a buoyancy force acting on the core, and the second part is a buoyancy force which is acting on the cube directly from the molten metal, right? This FB, which is the buoyancy force acting on the core, it's going to be the volume of the core times the rho, the mass density of the metal, negative the mass density of the core. And the core is going to be made of sand. So in many cases, we're going to consider the mass density of the core the same density of the sand of the casting, unless but actually they should be different, because the core in many of the cases it is made of a special sand that is a little bit stronger than the sand of the mold itself. But in many cases we can assume that they do have the same density, or if even they are the two different densities, one for the sand and one for the core, will provided. So you're going to use here the mass density of the core itself times g, which is the gravitational acceleration. We're going to end up with the buoyancy force acting on the core, as we discussed before. This Buoyancy force, this is the pushing from the metal acting on the core, then the core is gonna affect with the pushing as well on the coop. This Fm, this should be the total buoyancy force acting on the coop, plus the direct force that comes from a direct pushing from the molten metal directly acting on the coop itself, which is the buoyancy force on the coop. This one, it's gonna be considered as the rho GHA negative WC bar, where WC bar, this is C stands for casting. This is again the portion of the molten metal of the casting that is located in the coop that should be subtracted from the total buoyancy force here. If we added these together, we're gonna end up with the total buoyancy force that should be acting on the interface at the coop and the drag, or the drag and or in other words, this is the pushing the total pushing force due to the buoyancy force of the metal acting on the coop. Again, it has two parts in case that we do have a core, and there is an important notice here that this core, it should be located horizontal in the casting. Like you do have a core, and the core, it should be located horizontal in the casting. So there is a pushing acting from the buoyancy force or from the molten metal, push the core itself. This is the core, and then the core is gonna push the coop. This should be the coop up there. This is the coop. So there is another pushing comes from the core. This is only in case that the core is horizontal, but in case that the core is located vertical, so this pushing will be very negligible, or there is no pushing at all. So this FB term will be zero. It means that we're gonna proceed like, and we're gonna work like there is no core. Okay, as I'm gonna show you an example right now. This is for the Buoyancy force. Then also we discussed the design, and we discussed three methods, but we said that two of them that we're gonna use, the Chovanov's method and the Naval Research Lab. Naval Research Lab, this is a modification of Keynes method, so that's why we're gonna skip using the Keynes method, because it is not practical. The more practical version of this method is the Naval Research Lab method, and that's why we're gonna use it, the NRL method and the Chovanov's method. In Chovanov's method, it depends on the calculating the difference or considering the ratio or the difference between the solidification time needed to a complete solidification of the casting and the solidification time needed for a complete solidification of the riser itself. In general, the solidification time, according to the Chovanov's method, it should be constant, equals constant Cm, where this constant depends on the molten metal material. Like if it is made of steel, it will have a value. If it is of a different material, it will have a different value. There are some tables. I didn't provide these tables to you, but anyway, this Cm will be provided or given to you in the problem. So Cm, it is a material constant that depends on the molten metal material type. And V, this stands for the volume of the thing that you're calculating the solidification time for. If we are calculating for the casting, so you're gonna calculate the volume of the casting. If we are calculating the solidification time of the riser, this is gonna be the volume of the riser. The same thing for A, which stands for the surface area for either the casting or the riser, depending on which solidification time that you are calculating for the casting or the riser. And this N, which is an exponent, this exponent, we said that we're gonna use it as 2, but it would be different depending also on the material type, the casting conditions, the metal casting condition. But in many of the cases, we're gonna use it as 2, especially for steel castings. And this solidification time is gonna be in minutes, in case that you plug the Cm, the area in terms of centimeter square, and the volume in terms of centimeter cube, where Cm here, this is not centimeter. C is an uppercase, just to not be confused. This Cm in the green, this is the centimeter. This centimeter squared, centimeter cube, but Cm here, this is the constant of the molten metal material that it's gonna be provided, and it will be provided with a unit that fits with this empirical formula or this equation, kind of, to end up with the solidification time in terms of minutes. It means that this constant, it will be provided in terms of centimeter over or minute over centimeter. So this is for the solidification time. Also, in case that we do have a ratio between the solidification time needed for the riser over the solidification time of the casting, which this ratio should be bigger than 1. This R, it should be larger than 1. It should be larger than 1. Why? Because all the time I need to keep the solidification time of the riser longer than the solidification time of the casting. I need the riser to be liquid, and the liquid still as long as we can, to keep feeding the casting as long as there is cavities will show up under because or up on the shrinkage of the casting inside the mold cavity. And so according to the Cherepov's method, this VR over AR, where R stands for the riser, so this is the volume of the riser, the surface area of the riser squared, because we accepted that we said that we're going to consider this exponent as 2. So this is going to be square equal the ratio of the solidification time of the riser to the casting times the VC over AC square. It means that this expression has been derived from this relation. Simply, if you calculate the solidification time of the riser, so this should be the volume of the riser, the surface area of the riser. For the casting is going to be the casting and the casting. And you should understand that the CM for both the riser and the casting is the same, because the riser and the casting both will be filled with the same molten metal, so CM will be constant. Then if you divide this solidification time to this solidification time of the riser to the solidification time of the casting, we're going to end up with this expression. In terms of R, which is the ratio, this ratio it will be provided, or in other words, I would give you the solidification time needed for the riser and the solidification time of the casting. So you're going to divide both of them together to plug it here. You're going to end up with this expression that would be used for the calculation of the diameter and the height or the dimensions of the riser in terms of riser design. This is for the Cherepov's method. For the Naval Research Lab method, we said that this method depends on the calculation of a shape factor. This shape factor depends on the geometry of the casting. We don't care here for the shape factor about the, we don't consider the riser in the calculation of the shape factor. We just consider the casting dimensions. W, L, and T, these are equivalent length, width, and thickness of the casting. And K, this is, I didn't explain K to you in the previous video, but K generally, this is a geometrical constant that would be used for as a correction parameter for that depend on the complexity of the geometry of the casting. So this case, anyway, it will be provided to you. In many of the cases, it is just one. So that's why I didn't plug this K in the shape for the shape factor formula that we discussed in the previous video. But to consider more complicated shapes, this K would be provided in case that we do have, especially in case that we do have cores. So this is commonly known as the core factor or the geometry factor that depend on the complexity of the casting. As I mentioned, as I'm going to show you now how we're going to define this K. But anyway, in many cases, it will be provided. If it is not given to you, you're going to consider this K equals 1. Then once we calculate the shape factor, simply according to the Naval Research Lab NRL method, simply you're going to, with the shape factor, you're going to cut with a curve, and this curve will be provided to you. Then you're going to move to the left to find VR over VC. VC, this is the volume of the casting. VR, this is the riser volume. The riser volume definitely will be a function of its dimensions in terms of diameter and height. But the volume of the casting, it will be calculated as a number because the dimensions of the casting should be provided to you. It means that you're gonna end up with a value. From this value, you're gonna put it equal to VR over VC to simply calculate the volume or the dimensions of the riser. This is how the Naval Research Lab method works, as we explained over the previous video. But here let us discuss how we can calculate W, L, and T, the geometrical parameters. In case that we do have a sphere, for example, we can understand what does it mean L, W, and T, the length, width, and thickness. In case that we do have a cuboid casting, all of these are different shapes of the casting. In case that we do have a cuboid casting with a length A, B, and T, these two side dimensions in addition to the thickness T. So L, it will be the bigger value, the biggest of A or B. If B is bigger, so it's going to be L. If A is bigger, it's going to be L. W, it's going to be the second value. The third value, the smallest value, definitely it will go through, it will be given to the thickness. And for this case, the K, which is the geometrical constant, it's going to be 1. Why? Because in this case, there is no core. And even if there is a core here, this K, it will take a different value than 1. But again, generally, in case that K is not given to you, you're going to consider it 1. If it is given with a value, stick to it and use it as it is given. In case that would have the casting is a spherical shape, how much it should be L, W, and T? Both the three will be equal to the radius of the sphere of the casting, and K it will be equal to 1. In case that would have the casting is with cylindrical shape, you're gonna consider the W and the T, the width and the thickness equal the diameter of the casting, and the height it will be L. of the casting, it will be L, and in this case K is gonna be 1. And this is in case simply, basically in case that we do have a casting with a slender, and the slender is a little bit longer than the diameter, but generally we can consider even these two parameters, because the switching between L and W, it will not be that significant, because anyway they will be added together up there. For this case, and so as you can see, for all of these cases, this is standard shape. There is no core for all of these cases, so that's why this K is gonna be 1. But in case that we're gonna use a core, we have to do some correction here for this shape factor calculation. This is according to the Naval Research Lab method. So that's why this K will be given a value that is bigger than 1. It's gonna be bigger than 1, and it will be provided. So all the time K should be bigger than or equal 1. If it is not given to you, you're gonna consider K equals 1. This, we're gonna use this K, we're gonna need it, especially in case that the casting, it has like a hollow cylinder, like with an outer diameter D, and the inner diameter definitely is gonna be the core diameter. So C here stands for the core. Like because to form or to shape a casting, a hollow cylinder by casting, you should definitely use a core to form this internal opening, right? Internal hole. So this is going to be the diameter of the core, and the exterior is going to be the external diameter, and this is going to be the height. So simply we can assume that the length is going to be the height, and the thickness, this thickness is going to be the difference between d negative dc over 2, which is going to be d negative dc over 2, while the width is going to be like the circumference, which is the perimeter, by times d plus d over 2, which is going to be like the diameter of the average diameter, like the perimeter of the average diameter between these two diameters. Like we do have d and dc, so we're going to take the average and calculate the diameter, the perimeter of this diameter to end up with the width. And in this case, K, it will be provided with a value that should be bigger than 1 to compensate for the core in terms of the shape factor for the core existence, right? So this is how we can calculate the shape factor, and these are the main shapes that we're gonna consider for the castings. So simply, your objective is just to calculate the shape factor depending on the given shape of the casting. Then you're gonna use this figure to end up with the ratio VR over VC to come up with the dimensions or the volume of the casting. This is according to the Naval Research Lab. So these are all the formulas that we're gonna use here, and we're gonna use them to solve all of these different examples that we're gonna cover through today's video. Make sense? So let us consider this question number 3 in the exercise sheet 4. This is question number 3 in exercise sheet 4 for the Buoyancy force calculations. And this problem states that an iron casting, so the casting is made of iron. Iron, this is one of the iron, this is the basic, which is Fe, the basic element of the steel, right? So the casting is gonna be made of iron, and it has a shape of rectangular plate. So the casting, it should be rectangular plate. There is no drawing, but try to read the problem step by step. The casting is completely positioned in the drag. So it is completely positioned in the drag. It means that when we're gonna calculate the buoyancy force, there is nothing of the weight or of the casting that shall be subtracted from the buoyancy force. Why? It is completely located in the drag. And bored horizontally, it means that the rectangular shape will be located horizontally in the casting. Make sense? It is not standing vertical. The blade length, which is L, is given by 300 millimeter, the width 250 millimeter, and the thickness is 50 millimeter. So what does it mean? It means that the blade is gonna be located in the drag in the horizontal position, like it's gonna be aligned horizontally in this way. It is not standing as mentioned up there, right? Because if it is standing, the calculation of the projected area will be different, right? So this dimension is going to be 300 millimeter, 250 millimeter, and the thickness is given by 50 millimeter. The available flask dimensions were 400 length, 350 millimeter width, and height of 100 millimeter. This is the flask. And the density of the metal is given by 7 grams per centimeter cube, and the density of the sand is given by 1.6 grams per centimeter cube. So if I decided to plot this thing Here we are interested, this is gonna be the flask or the mold in general. Like we're gonna have the coupe on the top and the drag, and this is the line in the horizontal line in the middle. This is gonna be the parting surface, and the casting, it should be located horizontal, right, in the sand. This, all of this is just sand in this way here, and it's gonna be located horizontal. So what does it mean? It means that this dimension is gonna be 300 the length, and this thickness is gonna be 50. If we decided to look at it from the top, like you already drawing this, do you remember the fifth or the sixth step of the flask dimension in the sand mold design problem? You're gonna draw the flask or the mold in this way. If we're gonna look at it from the top, it will be seen like rectangular, and the casting will be in the middle like a rectangular shape, right? It's already located here. There is no need to add the A, B, and D dimensions as we did for the sand mold design process. The key idea here is just to figure out what is the projected area. This length will be 300, this length will be the 250 millimeter, and he gave us some dimensions to the flask. Like the flask, it will have a length. This is gonna be the width of the flask, right? And this is gonna be the length of the flask, which is already given by 400 millimeter, but the width was given by 350 millimeter up there, and the height, which is gonna be the height of the coupe, is already given by 100 millimeter. Make sense? And all of this is just sand. This is gonna be the coupe that we are talking about here, right? And this is gonna be 350 millimeter. So this is the drawing, the graphical representation of this problem, of this data. And he gave us here the mass density of the mineral equals to 7 gram per centimeter cube, and the mass density of the sand is given by 1.6 gram per centimeter cube. And there are some requirements. It is required to calculate the force acting on the upper surface of the mold coupe. It is required to calculate the force acting on the upper surface of the coupe or the mold coupe, which is Fm. This is the Buoyancy force. As given here, there should be some pushing, right? As we discussed before, this is the Buoyancy force. We would like to calculate this Buoyancy force. Remember that in this case, so the first requirement, we would like to calculate the Buoyancy force. Here, we don't have any core. There is no core. And in addition, the casting is completely located in the drag. This is going to be the drag, right? So what does it mean? It means that the Buoyancy force is going to be rho m times g times h times a. What is rho m? This is the mass density, but we do have two mass densities. Which one? The mass density of the molten metal. The metal is made of iron, and its mass density was given by 7 gram per centimeter cube. So the mass density is already given by 7 gram per centimeter cube. Keep all the dimensions in centimeters, as we mentioned before. So the gram, I'm gonna keep the gram as it is, and centimeter cube, I'm gonna leave it as centimeter cube, times g, which is the gravitational acceleration. We're gonna plug it as 981 to be converted into the centimeter, because it should be centimeter per second square. And this h, it should be the height of the cube, which it should be 10 centimeter, times the area. What is the area? It should be the projected area. What is the projected area? If I ask you to look to this casting, to this mold from the top, what is the area of the mold cavity that you're gonna see? Or in other words, this Buoyancy force is gonna acting over an area, right? Which area? It should be this projected area, which is gonna be the rectangular, which is gonna be the area on the top view of the mold. This is gonna be the projected area. If I ask you to calculate this projected area, it's gonna be 300 times 250, right? But convert the 300 millimeter into 30, because we are converting into centimeter, times the 25. So this value, this is the projected area, this is the height h of the coupe, right? And this is the gravitational acceleration, and this is the rho, the mass density of the metal. Make sense? If we did the calculations, we're gonna end up with the Buoyancy force in this case. Make sense? So to make the units make sense, or to make it easy for you to have the, because if I proceed in this units in this way, we're gonna end up with like kilonewton. But let us work conventionally. The gravitational acceleration should be 9.81, right? So it's gonna be 9.81, and this should be in grams, and this, all of these are centimeters. So you're gonna have here centimeter, centimeter, centimeter. We're gonna end up, this is gonna give us at the end like centimeter cube, right? And this should be like in meter per second square. If we use substitute with 9.81, this is gonna give us meter per second square. And this is gonna be given as gram over centimeter cube. So now the centimeter cube can be cancelled with the centimeter cube here. So we're gonna end up with grams times meter per second square. If this is a kilogram times meter per second square, gives us Newton, since we are seeking a force. So force, it should be in Newton in the metric system or the international system, right? So, but to convert this one into kilograms, we need it in kilograms, we have to divide here by 1000. So what you're gonna do, plug the G, the gravitational acceleration, as 9.81, and divide the density by 1000 to convert from kilograms to kilograms, and stick to all the dimensions to be in centimeters. So automatically, if you did the calculations, we're gonna end up with a number that it should be in terms of Newton. This is gonna give us the buoyancy force in terms of Newton, and this is gonna be the first requirement. Make sense? So if we did the calculations here, 25 times 30 times 10 times 9.81 times 7 divided by 1000, this is gonna give us 515.025 Newton. Make sense? So this is the amount of the buoyancy force. You could say that this is the amount of pushing comes from the casting or the molten metal inside the casting acting on the cube. And this is the first requirement, just to calculate this buoyancy force. The second requirement is just to calculate the weight of the sand cube. The weight of the sand cube. This cube is made of sand, and there is a flask, right? But here we would like to calculate first the sand cube. Just calculate the sand and the weight of an empty iron flask, and the weight of the flask. Remember that there is a flask already here. There is a flask for this cube. I'm gonna give it another color just to understand. There should be a flask here, right? This flask is made of iron, as he mentioned here. It is iron flask, right? So if I ask you what is the total weight of this cube? This cube, it consists of two things. Of the sand, because there is a flask that is filled with the sand, right? So it should be, there should be a weight of the sand. There is weight of the sand, and there is another weight for the flask itself. So he asked us to calculate two things. The weight of the sand cube, of the sand, just the weight of the sand, WS, how much it is, and the weight of the flask, assuming that the thickness of the wall of the flask, it is 10 millimeter as already given here. Make sense? So first of all, let us calculate the weight of the sand. What is the weight of any object? The weight, it should be the mass times the gravitational acceleration, right? And the mass of any object, it should be the volume times the mass density of this object. So let us calculate the cube, the sand inside the cube. What is the dimensions or the shape of the sand inside the cube? It should be cuboid. It should be like a cuboid shape. It has a length, it has a height and width. What is the length of the sand inside the cube? It should be the length of the flask, which is 400, and the width, it is 350, and the height, it is 100. Right? This should be the dimensions of the sand itself. So simply, I'm gonna calculate the weight of the sand. It should be the mass times the G, the gravitational acceleration. The mass, it should be the density of the sand, and the density of the sand is what it was given by 1.6 gram per centimeter cube, but this is the density of the molten metal, which is made of iron, right? Of the casting. But here we are talking about the sand times the volume of the sand of the cube, or you could consider that this should be the volume of the cube itself times the G, the gravitational acceleration. Make sense? So simply, the density, it is given by 1.6. I'm gonna divide by 1000 to convert from gram to kilograms, as we did here, times the gravitational, or times the volume of the cube. What is the volume of the cube? It should be the multiplication of the length times the width times the height, because this is the shape of the cube. So, but convert to centimeters, so this is gonna be 40 times 35 times the height, which is 10. This is the volume, times the g, the gravitational acceleration, which is 9.81. If we did the calculations, we're gonna end up with the weight of the sand. So this is gonna be 40 times 35 times 10 times 1.6 times the 9.81 divided by 1,000. This is gonna give us at the end 219.744 this should be Newton, because it is a weight. Make sense? So this is the weight of the sand. How about the weight of the flask? The flask, it has this shape. This is the shape of the flask. It's just an empty box. Like there is an edge, right? It's gonna be like in this way. The flask is just an empty box, right? That is already open from the top and from the bottom surface. So this should be the flask. So as you can see, the flask can be calculated as a cuboid, which is the external. The external of the flask, it has a length of 400 and width of 350, and its height, it is already 100, right? But in the meanwhile, it has a thickness of 10 millimeter all around. It's just 10 millimeter. This thickness as well is 10 millimeter. So if I ask you to calculate the volume of the ship, to calculate the weight, we should have the rho times g times v, the volume. So if I ask you to calculate the volume of this shape, so you're gonna have the volume of the external volume, which is 400 times 350 times 100. This is gonna be the external volume. Then you're gonna subtract the internal volume, because there is an empty cavity inside it, right? The internal volume will have a length. The length, it will be 400 negative 20. Right, the length of this edge, it will be, because you're going to subtract 10 from this side and 10 from the other side, right? So this dimension, it will be 400 negative 20, and this dimension, the internal dimension here, will be 350 negative 20, because there is 10 here and there is 10 from the other side. But the height, there is no subtraction for the height. The height still, the internal height as well is still 100. You got my point? So what we're going to do here, so simply this is going to be the mass density of the flask times the volume of the flask times g, the gravitational acceleration, right? How much is the mass density of the flask? He mentioned above here that the flask, it is made of iron, and the casting also is made of iron. So since both are iron, so the mass density of the molten metal, which is given for iron by 7 grams per centimeter cube, it works for both, for the casting and the iron, because they are made of the same material. And the mass density is a material property. Make sense? Otherwise, if the casting is made, if the flask is made of a material that is different than the material of the casting, so it means that the flask material density will be provided in this case. But here the density of the flask was not given, because simply it is made of the same material as the casting, iron and iron. So it means that we're gonna use the same mass density, which is 7. So definitely the rho here will be for the flask, which is gonna be 7 as well. It will be the 7 divided by 1,000 to convert from grams to kilograms, times the volume of the casting. Let us multiply times 9.81, which is the gravitational acceleration, times the volume of the flask. The volume of the flask, as we mentioned, it should be the subtraction. There should be subtraction here. It will be the external volume, which is gonna be 40 times 35 times 10. Here I converted all the dimensions into centimeters. They were given in millimeters. Negative. So this is the external volume, negative the internal volume. The internal length will be 400 negative 20, which is gonna be 380 millimeters. It means that it's gonna be 38 centimeters times the width, it is 350 millimeters negative 20, so it's gonna be 330 millimeters to, it's gonna be 33 centimeters times 10, which is the 100. The 100 won't gonna change. There is no subtraction. The height, the internal height of the flask it is typically the same like the external height of the flask. It means that it's going to be 100, it's going to be 10 in terms of centimeters. If we did the calculations, we're going to end up with something in terms of Newton. This is going to give us the weight of the flask. So let us do the calculation. Negative the 38 times 33 times 10 times the 9.81 times the 7 divided by 1000. This is going to give us the 100.258 Newton. Make sense? So this is for the second requirement. He required to calculate the force acting, the Buoyancy force, we already got it, which is the Fm, and the weight of the sand, the weight of the flask. Then how much of the necessary weight needed to keep the cube from floating? Because we don't have a pushing here. There is a buoyancy force acting on the cube, and there is a weight of the cube that already works against the buoyancy force. So there are two possibilities here. One option that the cube is heavier, it has a bigger weight than the buoyancy force, or the weight of the cube is bigger than the buoyancy force. So in this case, there is no need to add more weights on the top. Or the other option is that the buoyancy force is bigger than the weight of the cube. The weight of the cube, as we mentioned, it should be including the weight of the sand plus the weight of the flask, both of them together, right? So as you can see, we have a buoyancy force of 515 Newton, and the weight of the sand, it is 219, and the weight of the flask, it is 100. So the weight of the cube, the total weight of the cube, it will be the sum of these two numbers, which is 319 point something, right? So, and the buoyancy force is bigger. It means that the buoyancy force is gonna result in floating or moving. It will push up the cube and it would move the cube. So we have to apply weights on the top to overcome or to assist the cube to overcome the buoyancy force. So how much of weight is needed to be added? This weight, definitely it should be the difference. Difference between what? Between the weight of the cube and the buoyancy force. But in case that the weight of the cube is bigger than the buoyancy force, there is no need for weights. Okay, so the weight needed, it should be the difference between the cube and the weight of the cube and the buoyancy force. So simply we can write here that this is the third requirement. Okay, so the weights, it should be the buoyancy force negative these two weights, which is the weight of the sand negative the weight of the flask. So simply this is going to give us how much? The 515.025 negative 219.744 negative the 100.258. This is going to give us 195.023 Newton. This is the amount of force or amount of weight that needed that should be added. If you decided to convert this value into kilograms, simply divide by the gravitational acceleration, which is 9.81. This is gonna give us like 19.88 kilograms. So simply for this casting, if you put like around 20 kilograms on the top of this cube, you are in a good shape, no problem. The cube, it won't gonna be moved, all right, because of the buoyancy force. How about if we did the calculations and for some reason this number, we got it a negative. If we got this number negative, this indicates that the weight of the cube is bigger than the buoyancy force, and in this case, there is no weight is needed. Why? Because the weight of the cube, the total weight of the cube is bigger than the buoyancy force, and in this case, we don't need to add any weights. It means that the cube, it can work, it can overcome the buoyancy force. Make sense? So this is for this example and how it works and how we can do the calculation for the buoyancy force for the case that you have a casting that is of a rectangular shape and located horizontally in the mold. You would be given the same problem, but for example, for some reason, if we decided to cut this product vertically, not horizontally, so the different thing will be the projected area, how much it is. The projected area here, it is 300 times 250. But in case that it has been projected vertically, so you should understand which it should be provided to you over which side it should be casted or aligned, and in this case the calculation of the projected area will be different. Make sense? So this is for this example. So let us move to this question number 1 in the exercise sheet 4, also on the Buoyancy force. It is required to calculate the force acting on the inner surface of a mold cube. So the force acting on the inner surface of the mold cube, or the force acting on the cube, this is the Buoyancy force. Make sense? Due to the static pressure of an iron casting, the casting is made of iron, that is casted horizontally, it's going to be casted horizontally to produce a cylinder of external diameter of 500 millimeter and 400 millimeter internal diameter and 1000 millimeter length. So the shape of the casting is a cylinder with a hole. The cylinder has external diameter of 500 millimeter, internal diameter 400 millimeter, so there should be a core that should be used here. So the Buoyancy force, there will be pushing acting on the core, and the length of the cylinder is given by 1000 millimeter. Make sense? And it's gonna be casted horizontally in the casting. It's gonna be located horizontally. So first of all, the shape, just you can try to do some drawings. The drawings will not be provided to you. That this is the cylinder, and this should be the shape of the casting. This is the final product, right? This is what we would like to do by casting. It's gonna be with an external diameter 500, internal diameter 400, and length 1000 millimeter, and it's gonna be casted horizontally. I can cast this one vertically, but he mentioned here, let us do it horizontally. So how it works, then I'm gonna consider a similar example that it was vertical, right? But let us proceed that it is located horizontal. So for this case, if I ask you to draw the mold, so the mold is gonna be typically the same. It's gonna be, there is a cube, right? And there should be a drag somewhere, and this is gonna be the parting surface between the cube and the drag, and this is gonna be the top view of the shape. This is gonna be the top view of this shape, okay? Then the casting, it should be located horizontal as he mentioned here. It means that, let me use a different color for the casting. So if I ask you to do casting for this cylinder horizontally, where it should be the parting surface of this product, if I ask you to find the pattern, so the pattern, it should be the same shape, it should be the same shape, right? Typically, it should be cylindrical shape, but you're gonna get rid of the hole and you're just gonna add here some core prints because you're gonna use a core, right? And the parting surface, it should be in the middle. You're gonna slice it like a watermelon as we discussed before, right? You're gonna slice it into two pieces. One piece is gonna be located in the drag and the second piece is gonna be located in the cube. So it means that if we decided to draw this product, this cylinder that is gonna be casted horizontally in the casting, in the mold, it's gonna be represented in this way. Like half of it will be located in the cube and the second half of the cylinder will be located in the drag. And this should be like the core prints of the core. So this is gonna be like the pattern, how it's gonna be located inside the mold. And you could consider that this is like the mold here. I can even give some colors here. So this is gonna be like the mold cavity, right? But anyway, if this is the casting, there should be here a core, right? There should be a core that is gonna be used to form the internal opening. This is gonna be the core in the middle. So this is how it's gonna be the casting and the core located. Again, the core here, it will be horizontal. It means that there should be a pushing. If I ask you, there should be like a pushing force comes from the molten metal acting on the core, and then the core is gonna keep pushing on the cube, right? In the meanwhile, there is a pushing comes from the molten metal already directly acting on the cube itself. So there is direct and indirect effects of the metal. There is a direct effect from the molten metal as a buoyancy force acting on the cube directly, which is Fm1 according to the previous formulas, and there is an indirect effect comes through the core, like the buoyancy force, or the metal is gonna push the core, then the core is gonna push the cube as already represented here. And as you can see, half of the molten metal half of the casting will be located in the cube. It means that this half, it should be subtracted according to the formula that we discussed up there. We mentioned that for the calculation of the buoyancy force, in case that we do have a core, like this case, in case that there is a part of the casting that is located in the core, this part and the weight of this part, it should be subtracted. For this problem, we do have half of the casting is already located in the cube. So half of the casting should be subtracted from the total buoyancy force. In addition, the total buoyancy force acting on the cube, it will have also another term that comes from the buoyancy force acting on the core. This is another pushing but indirect one. This buoyancy force from the core, it should be the volume of the core times the density of the metal negative the density of the core times the g, the gravitational acceleration. So going back again to this example down here. So he gave us the mass density, the cube height. He gave us the height of the cube is already given by 500 millimeter. It is given by 500 millimeter. And this is how the casting is going to look like from this in the mold, inside the mold. If I ask you to find the projected area or the projected shape, just look at it from the top, it will be represented like a rectangular shape. From the top view, the casting will be seen like a rectangular shape, where this dimension, it should be the diameter, this dimension, it should be the diameter, which is 500 millimeter. This is the diameter of the slender, and this, it should be the 1000 millimeter, which it should be the length of this slender. If you're gonna look at it from the top, it will be represented as a rectangular shape with 100 times 500. This area definitely is gonna be the projected area that we're gonna use for the calculation of the buoyancy force. In addition, he gave us the mass density of the molten metal in addition to the mass density of the core, and he required to calculate the total force acts on the inner surface, which it should be the Fm, the total force. We said that it should be like Fb, the force, the indirect one that comes through the core, and the force, which is the direct one as a buoyancy force acting on the cube, right? How about the Fb, the force acting on the core? It should be the volume of the core times the mass density of the metal negative the mass density of the core times g, which is the gravitational acceleration. This is the buoyancy force acting on the core negative the weight or the portion of the metal that has been displaced by the, or you could consider that the buoyancy force is equivalent to the weight of the metal that has been displaced by the core. This is the volume of the core. Simply, the core, it has a cylindrical shape, right? With an inner diameter, so there should be a core here, right? This is gonna be the core. So the core will have an inner diameter of the cylinder, which is given by 400 millimeter, and the length of the core is already given by 1000, right? Which is it should be the same length as the cylinder. So this should be the volume of the core. So now so the volume, it should be pi over 4. The diameter of the core is going to be 400, so it should be times 4 square, because we are converting from millimeter to centimeter, times the length, which is 1000, so it should be 100. This should give us the volume of the core. Times the mass density of the metal, which is given by 7 divided by 1000, negative the mass density of the core, which is given by 1.6 divided by 1000, times 9.81, which is the gravitational acceleration. If we did the calculations, we shall end up with the mass density, the buoyancy force acting on the core. So if we did the calculation, we're going to end up with 6,650 Newton. Make sense? So simply, this is for the Fb. Then we're gonna calculate the Fm1. Fm1, it should be the buoyancy force acting on the cube. This buoyancy force, it should be the force comes from the Fm, which is rho m g h a, negative the weight of the portion of the casting that is already located in the cube. Here we have half of the casting is already inside the cube. It means that this half of the casting should be subtracted. So this is going to give us how much is the mass density of the metal is already given by 7 grams. So it's going to be 7 over 1000 to convert from gram to kilograms times 9.81 times the height of the cube, which is given by 500 millimeters, so it should be 50, times the projected area. The projected area is going to be 500 times 1000, so it should be 50 times 100. This is the area, the projected area, right? Make sense? So this is the first term, which is rho GHA, negative half of the weight of the casting. How much is the weight of the casting? The weight of the casting, or just see here, you should understand that C stands for the casting. The weight of the casting, simply, the casting, it has a cylindrical shape with internal opening. It is a hollow cylinder. So it should be the volume times the density of the casting, and the casting is going to be made of a metal with a mass density given by 7 grams per centimeter cube. So the weight, it should be the rho, the times G times the volume of the casting. So equals, which it should be the rho, the mass density of the metal, right? So this is going to give us 7 divided by 1000, which is the mass density, times 9.81, times pi over 4, times, what should be the volume of the cylinder? It should be the area, the volume, or the area of these two circles, like the external circle negative the internal circle. So it's going to be like pi over 4. The outer diameter square negative the inner diameter square times the length of the cylinder, right? So the outer diameter is already given by 500 and the inner diameter 400 and the length 1000. So it's going to be like 50 square, because we converted to centimeter, negative 40 square, the outer diameter, negative the inner diameter squares, times the 100, which it should be the length. Because it was 1000 millimeters, so it becomes 100 centimeter. If we did the calculation, we shall end up with the weight of the casting. So this is going to give us 50 square, negative 40 square, times shift pi divided by 4 times 100 times 9.81 times 7 divided by 1000. This is going to give us at the end 4,853.99 Newton. This is the weight of the casting. We're going to take half of it, half of this value that should be subtracted from this value. So we're going to end up at the end with Fm1. If we did the calculation, just calculate this term, negative half of this value, this is going to give us the Fm1. We're going to end up with 1,473 it is 14,725.5 Newton. This is going to give us the Fm1. Then we got the force acting on the core in addition to the force acting on the cube. So the total buoyancy force simply is going to be the sum of these two numbers, the 6,650 plus the 14,725.5. If we did the calculations, we're going to end up with 21.375.5 Newton. If you decided to convert this one into like weight, like mass, as in terms of kilograms, you can divide it by the gravitational acceleration. We're going to end up with 2138 kilograms. It means that the buoyancy force or the molten metal acting on the cube with the buoyancy force, this buoyancy force is equivalent to more than 2 tons of mass. Like pushing, it is a very high pushing force, so we have to overcome this pushing during the casting process, and this is for this example here. Make sense? Now in question 2 is going to be typically the same example, but except that we're going to do casting to this product but vertically. The same thing here, we did casting of the cylinder in the horizontal direction, so there was bushing over the core itself. But now how about if we're going to do casting to the same product but vertically? So we're going to reduce the buoyancy force kind of. So it is required again to calculate the force acting on the inner surface of the mold cube due to the static pressure of an iron casting. It is made of iron, so that's why the mass density is given by 7 grams per centimeter cube. This is the conventional density of the iron. that is going to be casted vertically to produce a cylinder with an external diameter 500 millimeter, internal diameter 400 millimeter, and length 1000 millimeter, and the height of the cube also is 500 millimeter. Typically the same problem, even the mass density of the core is given by 1.6 gram per centimeter cube, but the only difference is that it's gonna be casted vertically. So if we're gonna cut this cylinder vertically, it should be standing in the mold. So if I decided to draw the mold, the sand mold, this is gonna be the cube and the drag. This is gonna be the parting surface. If we decided to do casting to the product, for this product vertically, it means that it's gonna be located, completely located in the sand, in the drag. So this is gonna be the casting simply. And this is gonna be the parting, the core print, and there is another core print. Assume that this is the pattern, and you can simply get it out from the sand. All of this is just sand here, right? So it will be removed from the sand with no breaking, without breaking any sand. It means that we can consider that this is the parting surface, no problem. It's gonna be vertically casted in this way, and this core, it will be located vertical. The core, it will be located standing vertical in this way. So as you can see, the buoyancy force, so what is the pushing? To calculate the pushing or the force it will be just coming from this metal, right? This is just gonna be the pushing comes from the metal acting on the cube. Very simple. So it's gonna be, this is just this small portion, this area, and this area is gonna be the projected area. If I ask you to draw the top view of this shape, it's gonna be seen like two circles, right? With the same center point. So we're gonna have a big circle and the inner circle, right? And this is gonna be the projected area that I'm talking about. Like with external diameter 500, internal diameter is gonna be 400 in this case. So simply the buoyancy force, there is no pushing over the core. The core here has no clue, it doesn't work. I mean, there is no pushing acting on the core, so there is no additional buoyancy force comes through the core. The only buoyancy force comes directly from the metal acting on the cube, and the cube height is already given by 500 millimeters. So what does it mean if I ask you to calculate the buoyancy force? Simply the buoyancy force is going to be rho of the metal times G times H times A, negative the portion of the metal that is already located in the cube, but none of the metal has been located in the cube, right? None of the casting will be located in the cube. All the casting is already located, completely located in the drag, so there is no negative WC here. WC will be definitely zero. So how much is the density of the metal? The density of the metal is already 7 grams, so it should be converted to kilograms. So that's why I'm dividing by 1000 times 9.81. This is the gravitational acceleration times the height of the cube, which is 50 after conversion into centimeters, times the projected area. How much is the projected area? Simply, the projected area will be the area of these two circles, the external area negative the internal area, because this is the area that the metal will be touching and pushing from which the metal will be pushing on the cube. So it will be pi over 4 times the external diameter, which is 50 square, because after the conversion into the external diameter it is 500, and the internal diameter it is 400, right? 400. So 500 it becomes 50, so that's why it is 50 square, and the 400 becomes 40 square. This is the projected area, this is the area A. If we did the calculation simply, we're gonna end up with the buoyancy force acting on the casting in this case. It's gonna be like 9.81, or let's say calculate the square negative the 40 square times the pi over 4 times 50 times 9.81 times 7 divided by 1000. This is gonna give us at the end of 2426.998 Newton. This is gonna be the buoyancy force that acting on the cube because of the casting in case that we decided to cast this product vertically. So as you can see, the buoyancy force here, it is too much smaller than the buoyancy force in this case. Here it is 21,000. Right? But here it is just 2,400 Newton. So there is a big difference in the buoyancy force between casting the product vertically or horizontally. Again, here the core, it doesn't work. There is no pushing over the core. There is no subtraction of the half of the casting, because the casting, it will be completely located in the drag. And this is for the second, for this second question here on the buoyancy force. Now let us consider some examples on the riser design. Let us move to the riser design. So all the previous examples were just on the buoyancy force, how we can calculate the buoyancy force. Very simple. Now let us move to the riser design. Starting with question 1 in exercise sheet number 4, it is mentioned that a cylindrical riser, so the riser, it should be of cylindrical shape, right? This should be the shape of the riser. And conventionally, the riser, it should have like a cylindrical shape or a trapezoidal shape, like tapered shape, like a conical shape, or it would be any other shape. It is not necessary to be circular. It would be square. It would be rectangular base with extension like a pyramid shape, for example, kind of. But conventionally, and this is what we're going to consider, we're just going to assume that all the time it is cylindrical shape with a diameter. This is going to be the diameter of the riser, which is, we're going to give it like dr, and a height as hr, which hr stands for the riser itself. So a cylindrical riser must be designed for a sand casting mold. The casting is a steel plate. So the casting, it has a plate shape. This is the casting. So you should distinguish. In this type of problem, you will be given two shapes. It will not be drawn to you. The drawings will not be given, but you should understand from the statement. This should be the casting. It has a blade shape and it is made of steel with dimensions 75, 125, and 25 millimeters. So this is going to be like 125 millimeter length, 75 width, and definitely the thickness is going to be 25 millimeter. This is going to be the casting of, and this is the riser that we would like to design for the casting. As given here, all the dimensions of the casting were given, but the dimensions of the riser, we have no clue and we have to solve for it. Previous observations have indicated that the total solidification time for this casting is 2 minutes. Like, assume that we did this casting before and we had an experience with this casting, and we are pretty sure that this casting is going to be completely solidified into 2 minutes. 2 minutes, it is not a short time. 2 minutes is enough time. It would be like take 5 minutes or 6 minutes till solidification. But to cool down to the room temperature is going to take longer time, right? Much way longer time. But for the conversion from the liquid state to the solid state, it's going to take a few minutes, like 2 minutes, for example. This is according to the given data here. So the solidification time for the casting, it is already given by 2 minutes. What should be the solidification time of the riser? It should be definitely bigger than the solidification time of the casting. Why? We would like to keep the riser liquid for a longer time to keep feeding the casting. So the riser has a height equals its diameter. So he stated that the diameter equals the height of the riser. This is a given data. Determine the diameter of the riser so that its solidification time is 3 minutes. It should take a longer time with 1 minute longer. So what should be the diameter of the riser then? So since we are talking about, for the riser design, we said that we'd have two methods. The first method is the Cherepov's method, and this method depends on the difference between the solidification time of the riser to the solidification time of the casting, right? And he gave us the solidification time of the riser and the casting. Then here, he asked us to find the riser diameter if NRL method, which is the Naval Research Lab method, is used. So it means that before this statement, initially you have to solve the problem. Initially, you have to solve the problem using the Cherepov's method to find the diameter. Then once you find the diameter, you're gonna do design and find the diameter of the riser, but using the Naval Research Lab method. Why? He didn't ask us, he didn't mention directly use the Cherepov's method to find the diameter of the riser. He didn't mention that. But this should be understood. Since we are talking about solidification time, how much is the diameter? So intuitively, we are talking about Cherepov's method. So he asked us, he required, this is the first requirement, and this is the second requirement. it is required to determine the diameter of the riser so that its solidification time is 3 minutes bigger than 3 minutes. It means that 1 minute higher than the 2 minutes of the casting solidification time, right? So since we are talking about solidification time, it means that initially for the first requirement, you have to use the Cherepov's method. Make sense? You got it? Then we can simply solve the problem using the Navarre Research Lab. This is for the second requirement. So for the first method, and this is what we're gonna start. We're gonna start with the Cherepov's method. Make use of the solidification time that already given to us. So simply, we said that, or according to the Cherepov's method, we said that the volume of the riser divided by the surface area of the riser squared, it should equal R times the volume of the casting divided by the surface area of the casting squared, right? How much is R? R, it should be the ratio of the solidification time of the riser to the solidification time of the casting, which is already given by 3/2 minutes. So it means that this ratio is gonna be like 1.5. Then you're gonna plug 1.5 here for this one, but your objective is just to calculate the volume of the casting and the surface area of the casting first, in addition to the volume and the surface area of the riser. So how much is the volume of the casting? The casting, it has a cuboid shape, so its volume, it's gonna be the multiplication of these 3 dimensions. So it's gonna be 125 times 75 times 25, but you're gonna multiply it times -3 to convert into centimeter cube. This is gonna give us something in terms of centimeter cube. So if we did the calculation, this is gonna give us 75 times -3 is gonna be the 234.375 centimeter cube. How about the surface area of the casting? The surface area of the casting is gonna be this area times 2, because there are 2 surfaces for this one, and this area times 2, and this area on the top times 2. Very simple, right? 6 faces, right? 6 surfaces. So the first, it means that we're gonna have the surface area of this casting, it will be 2 times, the first area is 125, so you can convert to centimeter directly, so it's gonna be like 12.5 times 2.5, which is the thickness, right? Times 2, plus the second area, which is 7.5, because it is 75 divided by 10, times 2.5, plus the third area, which is the area on the top, which is 125 times 75, so it's going to be 12.5 times the 7.5 to convert to centimeter. If we did the calculation, we're going to end up with something in terms of centimeter square, and this is going to give us the area, definitely. So this, it will be 12.75, 2.5 and times 2.5 plus the 12.5 times the 2.5 times 2. This is gonna give us the 287.5. This should be the surface area of the casting. How about the volume of the riser? The riser, it has a cylindrical shape, very simple. So its volume, it's gonna be the area of this cylinder, of this circle times the height. So it's gonna be pi over 4 dr square times hr, right? And since dr and hr are the same and we are seeking the diameter, so this definitely can be written as pi over 4 dr cube. This is for the volume. The surface area of the riser is gonna be. So this is a little bit tricky here, and there is something that we consider when we calculate the surface area of the riser. If you remember, for the riser, we said that the riser, it would be located on the top of the casting to keep feeding the casting, or it would be on side. If you remember that, we explained over the slide that the riser, it could be located on the top of the casting. So this is gonna be the casting, and the riser is gonna be located already on the top of the casting. This is gonna be the riser, and this is gonna be the casting, right? This is one option, option 1. Or the option 2, that you just gonna assume that I'm gonna put the riser on the side. This is gonna be the riser, and it's gonna be set up on the side of the casting. It means that this is gonna be the casting in this way. It means that the riser it will not be on the top. This is gonna be the second option, right? So for the first option here, if I ask you to calculate the surface area, this AR in this formula, this AR, it should be the area of the riser that is exposed to the sand, that is subjected to the sand, that is touching the sand. So AR, it should be the surface area of the riser that is touching the sand or is exposed to the sand, right? So simply, for this case, which surfaces that will be touching the sand? This surface, this cylindrical surface, and just this circle on the top. But here, so it means that for this case, we'd have only two areas. But for this one, we're gonna have this cylindrical surface will be subjected, will be touching the sand, in addition to this surface on the area on the top, in addition to the surface down here, because all the way will be there, all around will be sand. Make sense? So in case that the riser is going to be located on the top of the casting, there will be one circular area of the riser that it will not be exposed to the sand, and it should be not included, or it should be excluded from the calculation of the surface area of the riser if you decided to put the riser on the top. But if you decided to put the riser on the side, so in this case you have to consider all the areas of the riser. It will have two circles, one on the top, one on the bottom, in addition to the cylindrical surface, external surface of the riser itself. It depends whatever is going to be on side or on top of the casting. Make sense? So if I decided to you, if I defined, if I stated in the problem that the riser, it should be, it's going to be located on the top of the casting. So you have to consider that there is one circular area of the riser that should not be included in the calculation. Should be excluded from the surface area of the riser calculation. But if I said on side, you have to consider all the surfaces area. If I didn't mention, as in this case, here I didn't mention to you, whatever is on side or on the top, you have to define to me whatever it is on top or on side. You have to mention. You have to let me know. Is it on top or is it on side? Then you're going to do the calculation. It's up to you to choose either options. Okay? I didn't explain. Definitely, for sure, this depends on the practical use and depends on your experience. You're going to find that based on your experience, for example, if this casting is large size and means that this area is large, it is better to have the riser on the top of the casting. In some other cases, you may decide to have this riser on the side. So you don't have this experience yet, so you can assume anything and proceed with, but you have to let me know which option that you proceeded with, riser on the top or riser on the side. It's up to you. So let us proceed with this one. Let us assume that we're going to consider riser on the top. So it means that I'm going to exclude the area on the bottom. This bottom area of the casting will be excluded from, of the riser will be excluded from the surface area calculation. So we're going to end up with just two areas. The circular area on the top, which is going to be pi over 4 d squared. So it's going to be pi over 4 dr squared. This is the area on the top, plus the cylindrical area. The cylindrical area is going to be the perimeter times the height. So it's going to be pi dr, which is the perimeter of this circular base, times the height, which is hr. Remember that hr is already given by the same diameter as d, so I can replace this one as dr squared. If you add it, we're gonna end up like 5 over 4 by dr squared. This is in terms of the diameter. So your objective is just to find the riser volume in terms of the diameter, in addition to the the surface area in terms of the diameter of the riser. Make sense? Then your objective is just to plug these 4 data here. So VR, we got it by this term. So the first term will be pi over 4 dr cube divided by AR, which is going to be 1.25 by dr square, right? Squared. This is the first term, the VR over AR equals the R that we already calculated by 1.5 times the volume of the casting divided by the surface area. This is the volume, this is the surface area. So it's going to be the 234.5 375 divided by the area, which is 287.5 squared. If we did the calculation to this expression, we'd have only one unknown, which is dr. Simply dr squared will be cancelled with the cube, and pi, or no, just do pi can be cancelled with the pi. Then do the calculations, you're gonna end up with the diameter of the riser in terms of centimeter. Why centimeter? Because we changed all the units into centimeter. We are using centimeter, so we're gonna end up with the diameter of the riser in terms of centimeter. This definitely is gonna give us 23435 divided by 285.5 squared times 1.5. Then on the left side we do have like 0.525 divided by 1.25 squared, right, times dr. So this should be multiplied times this value, so we're gonna end up with like 0.0398 centimeter. If you multiply it times, no, this value should be squared, then so it's gonna be like, I'm sorry, this should be like 0.199 centimeter, kind of, it is too small, so I'm gonna check this value. Yeah, if I have checked this value, it should be like 4, it should be 4, it should be 4.99. It should be 4.99 centimeter, which is gonna be like around 5 centimeter. If you decided to convert into millimeter, so it should be the diameter should be 50 millimeter, and dr it should equal to hr as he mentioned or stated in the problem with this value. So this is for the riser design according to the Cherepov's method. Now we're gonna repeat the same, and we calculate dr and hr, but using the Naval Research Lab. Naval Research Lab, if you remember, depends on the calculation. So the second method here, the NRL method, right? This method depends on the calculation of a shape factor and using a curve like this one. This curve will be given to you on the exam or the problem. Again, we said that we're gonna get this curve using some experimental measurements that this lab already provided for different castings. So assume that this curve is already provided to you, and the vertical axis is VR over VC, where R stands for the riser. This is the volume of the riser to the volume of the casting, and the horizontal axis, this is the shape factor. So your objective is just to calculate the shape factor of the casting. The shape factor, it should be L plus W divided by K times T. We said that this K would be, this is like a core factor, and K that would have a core, so we have to consider this factor. But here there is no core, and we said that for the casting with this cuboid shape, this K is gonna be 1. And the length is gonna be definitely 125 millimeter, and the width is gonna be 75, the thickness is gonna be 25 millimeter. Very simple, we can calculate the shape factor. So this is gonna be the 125 plus the width, which is 75, divided by K is already 1, divided by T, which is 25. It doesn't matter whatever you do, you convert it into centimeter or leave it millimeter, because this is a factor, so this is dimensionless. You're just gonna end up with a value as plus 75 divided by 25. This is gonna give us 8. Then you're gonna use this figure, and we got the shape factor by 8. So your objective is just to draw a line, vertical line from the shape factor equals 8 till you hit the link, till you intersect with the link. From this intersection point, you're gonna move to the left till you're gonna find a value for the VR over VC approximate value. So it's gonna be like approximately from this figure, from the figure or from the curve, we're gonna find for the shape factor equals 8, we're gonna find VR over VC equals like 0.38, kind of. If you got it like 0.4, 0.37, it doesn't matter, it's gonna be very close. Then your objective is just to do the calculation. So the volume of the casting, which we already got it up there, right? The volume of the casting, we got it in terms of the diameter as pi over 4 dr cube. So it's gonna be pi over 4 dr cube. It should equal to the 0.38 times the volume of the casting. The volume of the casting we calculated by 234.375. So it's going to be 234.375. If we did the calculations, we can simply find the diameter of the riser in terms of centimeter, right? From this expression. So if we did the calculation, 0.38 times 234.375 divided times 4 divided by pi and the 1/3, this is gonna give us 4.84 centimeter, which definitely I'm just gonna assume that it's gonna be very close. We got it up there by 4.99, we are getting here 4.84. So it is very close. As you can see that the two methods almost they're gonna give the same result. So we can assume that this is like 48.4 millimeter, or simply you can assume that the diameter of the riser equal the diameter equal 50 millimeter. This is, for example, this is how I'm going to design, because it is not necessary, but this is the number that you should provide it to me, right? But 50, this is what I'm gonna consider in terms of practical use or design of the riser itself. Make sense? So this is for this example, simply how we can do calculation for the riser according to the Cherepov's method and the Navar Research Lab method. Now let us consider this example, question 5. Here, 3 steel castings. So the castings are made of steel, and there are 3 different castings. So 3 steel castings have the same volume of 1000 centimeter cube. So all the castings, they are identical in one thing, in that they do have the same volume as 1000 centimeter cube, but different shapes. One is a cube, one is a sphere, one is a cylinder. So we do have 3 castings. Here we are talking about the casting themselves. But 3 different castings, the common between them is that all of them, they do have the same volume, which is 1000 centimeter cube, but different shapes. One is cube, one is a sphere, one is a cylinder with height. The cylinder, it has a height that is equal to its diameter. The cube, it has only one dimension. That, for example, if I ask you to draw a cube, the cube is gonna be this shape, right? And we can assume that the side edge of the cube is just A. So A, all these dimensions will be A. For a sphere, it has only one dimension, which is the radius or the diameter of the sphere. But for a cylinder, it has 2 dimensions, right? 2 things, diameter in addition to height. So that's why he said that the diameter is equal to the height. So both are D or both are H, kind of. Make sense? Its height is equal to its diameter. All casting are bored in the same mold and at the same boring temperature. Like we would like to make all of these casting of the same material, and they're gonna board in the same casting under the same condition, under the same boring temperature. So to achieve similarity between the material, the casting and everything. So he asks us which casting that will solidify first and why. Which casting that will solidify first and why. Here, he didn't require anything regarding the riser. So, for this type of problem, as we mentioned, what makes the casting solidify, that the sand itself, it works like a heat sink. It takes from the temperature, it takes from the heat of the molten metal. So, if the molten metal is exposed to more sand, or the surface area or the exposure of the molten metal to the sand, it is higher, it's gonna solidify faster. It means that the solidification time will be shorter. So that's why he asked here about the solidification time for all the 3 castings. Which one will solidify before the other one? Make sense? So it means that to judge on this thing, your objective is just to figure out which one of these castings will have a bigger surface area, who has a smaller surface area, so we can arrange them based on the surface area in terms of the solidification, since they are common in terms of the volume. The other option is just to calculate the solidification time for each one based on this formula. According to the Cherepov's method, we said that the solidification time generally it is Cm divided times the volume over the surface area squared, of the casting or the riser or whatever, all of this casting. So your objective is just to calculate the volume of the casting, which is already given to all of them by 1000 centimeter cube. Then your objective is just to calculate the surface area of the castings. Then plug it here, you're gonna calculate the solidification time. Then you're gonna see which one is gonna solidify first, second, and third. Arrange them according to the solidification time. So, but you should understand that the CM, it should be the same for all of the three. Why? Because they're gonna be casted of the same material in the same mold under the same boiling temperature. So the same casting conditions are the same for all of the casting. It means that this indicates that this CM will be the same for all of them. Make sense? So the key idea here, as I mentioned, that what distinguishes the solidification time of this one to this one to this one is the surface area. The one that is gonna with a bigger surface area, it means that it will be exposed to larger sand. It means that it's gonna cool down faster than the others. It means that its solidification time is gonna be shorter than the other, and this is gonna be the first one to be solidified. So which casting that will solidify first, or in other words, put these casting in an order according to their solidification time, how we can arrange them. Which one will solidify first, which second, which third? Let us do the calculations. So to calculate the surface area for any one of these casting, we should have the diameter, the radius, and the A, the side length of the cubic shape. But the volume is already given up there, right? So from the volume, we can come up with the A, how much it is. We can come up with the R, how much it is, and so on. So let us split the page into three parts here. Work over the three casting. Here we're gonna work on the cube, which is just a cuboid shape with a side edge, or a cubic shape with a side edge A. So the volume of the casting, definitely it will be A cube, which is already given by 1000 centimeter cube. So we're gonna conclude that it's gonna be 10 centimeter. Very simple. Make sense? How about the second casting, which is the sphere? The sphere has a radius of R. So the volume of the casting is gonna be, the volume of the sphere is gonna be 4/3 by R cube. If you remember this expression, this should be 1000 centimeter cube. So simply we can end up with the R, how much it is in terms of centimeter. Make sense? So the R, it will be 6.2 centimeter if you did the calculation. This is gonna be 1000 divided by 4 times 3 divided by pi, and 1/3 is gonna give us 6.2 centimeter. This is R. For the cylindrical shape, with the diameter equals the height, the diameter equals the height. This is for the cylinder, which is the third casting, and this is the second casting, which is the sphere. And D equals H, as he mentioned. The volume of the casting, it should be pi/4 D squared times H, which should be D cube. It should equal to the 1000. If we did the calculation, we're gonna end up with the diameter in terms of centimeters. So the first thing is just to find the dimensions of this casting. So the diameter of the casting in this case is gonna be 10.84 centimeter from the calculation. Very simple. Then your objective is just to calculate the surface area of this casting, how much it is, the surface area of this one. The surface area of the cube is gonna be 6 times the square, A square, right? Because each one of this area just A square times 6 faces. So this is gonna give us 600 centimeter square, right? Because this is 10, so it's gonna be 100 times 6, it's gonna be 600 centimeter square. How about the surface area of this casting of the sphere? The surface area of the sphere is gonna be 4 times the area of the circle, which is 4 by R square. So it's gonna be R is, we got it by 6.2. If we did the calculations, we're gonna end up with 483 point something 1 centimeter cube. This is the surface area of the sphere. How about the surface area of the cylinder? The cylinder, it has an area on the top, and there is another circular area here on the bottom, right? We have to consider all the areas here. This is not a riser. This is the casting itself. So I have to calculate all the areas. So we have one area on the top, one area in the bottom, so double areas in addition to the external area, which is the cylindrical area. So it's going to be 2 times. So it's going to be 2 times pi over 4 d square. This is the area on the top and area on the bottom, plus the area, the cylindrical area, which is going to be pi d times h, the perimeter times the height, because the expanded shape of this cylindrical shape is going to be like a rectangular shape with a length of pi d and a height of h, or width of h. If we did the calculation, h definitely is going to be d, and we got d by 10.84. If we did the calculation, we're going to end up with the surface area of the cylinder, which is going to be 553.7 centimeter cube. So as you can see, we did the calculation, we end up with the surface area. We found the dimension first, then we calculated the surface areas. So as you can see that the cube is the one with the largest surface area. It means that the cube, it should solidify first. Then the cylinder, because its area comes the second, and the third surface area, the smallest one, is for the sphere. Indicate that the sphere is gonna take longer time till the solidification under the same condition as the 3 casting. So if we decided to calculate, the solidification time of the 3 casting, as we mentioned, the solidification time, this is the expression for the solidification time, Ts. It should be Cm times Vc over Ac squared, right? So how much is the solidification time here, the Ts? It should be Cm times 1000 over 600 square, right? So it's going to be something in terms of Cm. So it's going to be 1000 divided by 600 squared, right? So this is going to give us 2.78 Cm. This is not centimeter, this is the constant Cm, which is the constant of the metal. And the solidification time in this case is going to be the same Cm, but 1000 divided by the 483.1 square. If we did the calculation, this is going to give us like 4.3 Cm, and the solidification time here is going to be the same Cm, but 1000 divided by 553.7 square. If we did the calculations, we're going to end up with, for the 3.3 Cm. So as you can see, since all of them, if I ask you just to find the solidification time of the cylinder, to the solidification time, or the solidification time of the cylinder, which is going to be like 2.78 Cm, to the solidification time of the sphere, which is 4.3 Cm, to the solidification time of the cylinder, this is the cube, I'm sorry, this is the sphere, this is the cylinder, 3.3 Cm. Simply we can cancel the Cm with the Cm with the Cm, since they already have the same values. So as you can see, this is gonna take longer time, the sphere, and it means that, so we're gonna end up that the solidification time of the sphere is gonna be the largest one, and the second one is gonna be the solidification time for the cylinder, right? And it's gonna be larger than the solidification time of the cube. So what does it mean this? It means that the cube, it will be first. So cube will be solidified first, cylinder second, and sphere will be third. Make sense? It means that the sphere is going to take a longer time, and the second time is for the cylinder, and the cube, it will be the first to solidify, because it's going to take a shorter time till the solidification. This is for the first requirement, which one solidify, or the arrangement, the order of this casting in terms of solidification. Then it is required to determine the relative solidification time using the Cherepov's method, and this is what we got here. This is the relative solidification time. The time of the sphere to the time of the casting to the time to the cylinder to the time of the cube, the solidification time of the cube to the solidification time of the sphere to the solidification time of the slender, we got it. So the relative, so this is for the second requirement, the relative solidification time. So for the second requirement, the relative solidification time is gonna be like cube to the slender to the to the sphere. In the middle we just used the sphere to the slender, just to stick to the same arrangement that we put up there. It's gonna be like 2.78 to the 4.3 to the 3.3, right? This is for the second requirement. The third requirement, it is required to calculate the riser for each casting using the Naval research method. It means that this figure, there is a curve that should be provided, and your objective is just to calculate the shape factor for each one of these castings. So we're gonna do the same. Assume that this curve is already given to you for this steel casting. Okay, let us consider this curve here on the side, and then we're gonna calculate, we're gonna continue the same. So we do have three castings, right? We do have three castings, and our objective is just to calculate the shape factor for all of the three castings. The first one is the cuboid shape. So what should be the shape factor for this one? The shape factor is going to be LW over T times K in the denominator. So the shape factor for this one will be L plus W over KT, right? K definitely is going to be 1. L, it should be L, W, and T all are equal to A, right? It should be A plus A over A. So it's going to be like 2A over A. So it's going to be just 2. So the shape factor for this casting is going to be 2. Next, we're going to calculate the shape factor for the sphere. The shape factor for the sphere, we said that like the length for the sphere, the length and the depth and the width and the thickness both are equal to R. So we're going to end up here that L plus W over T and K definitely will be 1. It will be R plus R over R. So it's going to be like 2R over R is going to be 2 as well. For the shape factor, for the slender, the L and W will be, the W and T will be D, and the height will be L. The L will be the height. So this is going to give us the shape factor as L plus W over T, and K definitely will be 1. So this is going to give us the L will be LH, which is D, and the W will be D, and T will be D. So the shape factor will be 2 as well. So as you can see, all the three castings, they do have the same shape factor according to the Naval Research Lab method, right? All of them, they do have the same shape factor, and which is equal to 2. So directly, if we're gonna go to this figure, somehow, let us assume that this number do changes, because there should be another figure. Assume that this is like 1, 2, 3, 4, 5, 6, 7, and 8, for example. So simply, according to this method, when the shape factor is 2, if you're gonna go up and intersect with the curve, we're gonna end up with like around from the curve, we're gonna end up that VR over the volume of the casting, it should be 0.38. So we're gonna conclude that the volume of the riser, it will be the multiplication of the volume of the casting, which is already given by 1000, because all of them, they do have the same volume as 1000 centimeter cube as mentioned above, right? So if we did the calculations here, we're gonna end up with the volume of the riser is gonna be definitely 1000 times the 3 it's gonna give us the 380 centimeter cube. The same volume is gonna be for the other cases. The volume of the riser as well will be 380 centimeter cube, and here the volume of the riser is gonna be 380 centimeter cube, right? So this is the volume of the riser in the three castings will be the same. So this indicates that the three castings will require the same riser according to the Navarre Research Lab method. According to the Navarre Research Lab method, since they all have the same factor, so it means that the same casting can be used for any one of them, right? And even the diameter, if I ask you to calculate the diameter of the casting, assuming that the casting, it has a cylindrical shape, cylindrical shape, so the diameter, the volume of the riser, it should be pi over 4 d cube, since assuming that the riser, it has the same diameter. This is the height of the riser, HR, and the diameter is dr. So assume that dr equals HR, so we're gonna end up with this volume. So definitely dr, it will be, if you just VR, we already got it by 380 centimeter cube, so it's gonna be this value times 4 divided by shift pi and 1/3. This is gonna give us the diameter as 7.85 centimeter, which is gonna be like 78.5 millimeter. So as you can see, the same riser should be used for all of the castings, since all of them do have the same volume, and since all of them do have the same factor, shape factor, according to the Navarre Research Lab method. But according to the Chevernov's method, different castings, different risers should be used for the 3 castings. Like this casting will have a riser, will use a riser that is different than the riser of the sphere, that is different than the riser of the slender. This is according to the Chevernov's method. Why? Because the Chevernov's method depends on the time relative, the difference or the ratio between the solidification time of the riser to the solidification time of the casting. So since we do have different solidification times between the 3 castings, this indicates that according to the Chevernov's method, the 3 castings will use different risers. But according to the Navarre Research Lab method, the 3 castings will use the same riser, and this doesn't make sense, because what makes sense that definitely the 3 castings will not solidify in the same time, even if they do have the same volume. So this also indicates there is a drawback somehow in the Navarre Research method, but the common method that can be applicable to any case is the most general method, is the Chevernov's rule or the Chevernov's method, and that's why it is preferred over any other method. Make sense? So this is for this example here. He required us to calculate the riser for each casting according to the Navarre Research Lab method. We got that all of them, they do have the same riser, which kind of doesn't make sense or just acceptable, but this is not accurate, and the Chevernov's method is preferred in this case over the Navarre Research method for this example. Make sense? Now we're gonna move to the last part, which is the Sprue design, the down sprue design, and how we can do calculation for the down sprue according to this example. There is like 2 examples or 2 problems in the exercise sheet. This is one of them. Here he gave us the rate of flow of a liquid metal. This is here. Now we're gonna move to the sprue design. This problem is regarding the sprue design. And this is gonna be the last example of today's video. So the rate of flow, which it should be Q. So here he talks about Q. This is the rate of flow of liquid metal into mold is 2 liter per second. So this is the Q is already given by Q is given by 2 liter per second. The diameter of the down sprue at the top, the diameter of the down sprue at the top equals 35 millimeters. So it is 35 millimeter. We can convert into centimeter directly by dividing by 10. And the height of the sprue, the height of the sprue is given by 250 millimeter. So we can convert into centimeter as 25 centimeter. Make sense? What should be the diameter at the bottom of the down sprue to avoid aspiration? And what does it mean, aspiration? For sure, what does it mean, aspiration? We knew that it is breathing air to fill into the mold cavity, and to avoid aspiration, we have to use taper down sprues, right? So what should be required here? What should be the diameter of the down sprue at the bottom? How much it is? So it is very simple calculation. We can use this expression that the area at the bottom to the area of the at the top, it should equal to the square root of ht divided by hc, or or hb, right? We can use this expression in case that the heights, these two heights already given. We do have the area at the top. We can calculate the area since the diameter at the top is already given. But how about these edges, these heights, and we would like to come up with the area B. So we can use this one, but we do have only one height, which is the height of the down sprue, right? This is the height of the down sprue, is the only thing that is given, but we have no clue how much is the HT, also how much is HB. It is not given in this case. So we can find these relations using the Q, which is the volume flow rate that already given to us here by 2 lit per second, as I'm gonna show you. So again, as I mentioned, the objective is just to find HT and HB. So just if you it is preferred to draw the boring cup along with the down sprue, the drawing that we represented up above before. Like this should be the boring cup and this should be the down sprue. Okay, it should be tapered somehow, right? And we said that we're gonna define here a datum. This is gonna be the datum for this one, and there should be some heights. So one height is gonna be HT. This stands for the height of the boring cup. In addition to this total height, which is gonna be HT, this is the height of the top surface or the top area from the datum, and this is the height of the bottom area from the datum, including the boring cup. This is gonna be the cup, the boring cup, right? And this should be the sprue. And this should be here, this is the AT and VT, and this should be here the VB and AB, which is the velocity at the bottom and the area, the bottom area of the down sprue, right? And he gave us here, this is one of the given data, he gave us that the height of the down sprue, is 250. It means that this height is already given by 250 millimeter. Make sense? So simply HB, it should be the 250 plus HT. So we have to seek a value for HT. We have to find a value for HT. HT, we can get it from this formula. Like if you remember that VT, it should equal to the square root of 2G times HT. The same thing for VB, the velocity at the bottom, it should equal to the square root of 2G HB, right? But here we are seeking the HT. We would like to find HT, so we have to find VT first, the velocity at the top. The velocity at the top, we can find it from Q. Q is already given here. Q is given by 2 lit per second, right? And it should equal to the area at the top times the velocity at the top. In the meanwhile, it should be area at the bottom, the velocity at the bottom. We have no clue about for these values, so ignore these values here because the area at the bottom, it is not known, it is required anyway. The same thing for the velocity. So, and we are interested to find VT. So from this expression, we can find VT. So simply VT, it will be Q divided by the area at the top, right? The Q, it should be 2 times to convert from liter to centimeter cube, you're gonna multiply it times 1000. This is just to convert from liter to centimeter cube divided by the area at the top, which is gonna be pi over 4, the diameter squared. The diameter is already given by 3.5 centimeter. Here, this value, this 1000 to convert from liter to centimeter cube, right? So it means that we have to, we should have this one as centimeter. So it's going to be like pi over 4, the diameter, which is already given in centimeter as 3.5 centimeters. So it's going to be 3.5 centimeter square. If we did the calculations, we're going to end up with centimeter per second. This is going to be the velocity of the molten metal at the top of the down sprue. So it's going to be 2000 divided by pi multiplied by 4 divided by 3.5 squared. So this is going to give us 207.87 centimeter per second, right? This is the velocity at the top, simply we're gonna use this one to find HT. So simply HT, the height of the boring cup, which it should be the height of the boring cup, is gonna be just the square of this term. So it's gonna be VT squared divided by 2G, right? So VT we got it by 207.87 squared, and this should be divided by the 2 times the G, which it should be 981 here to substitute for 981 to convert into centimeter. So this is gonna give us the or it's gonna be 81.1 to convert into centimeter, 98.1 to convert to it's gonna be 981 to convert, because this should be 9.81 in terms of meter per second square. To convert to centimeter is gonna be 981, right? Because you should multiply by 100 times 100. So this is gonna give us, if you did the calculations, divided by 2 divided by 981, this is gonna give us 22.024 centimeter. This should be the HT, which is the height of the cube, right? I'm sorry, this should be the height of the cup, the boring cup height, which is HT. So HB, the total height, it should be the 250 or the 25 centimeter plus the HT, because we already working in centimeter. So directly HB is gonna be the HT plus the height of the down sprue that already given. So HT is, we got it by 22.024 plus the height of the down sprue, which is 25 centimeter. If we did the calculations, this is gonna give us the 47, around 47 centimeter. Then your objective is just to plug HT and HB into this expression to end up with the area of the bottom of the down sprue. So the bottom area of the down sprue over the top area, it should equal to the square root of HT divided by HB, and we got this ratio. So HT, we got it by the 22, right? Point something, 24, divided by the 70, the 47. If we did the calculations, we can simply end up with the area of the bottom, because the top area, we got it before. The top area of the down sprue, we got it here somewhere. Yeah, it should be this top area. It should be pi over 4, 3.5 squared, because the diameter of the down sprue on the top is already given. If we did the calculation, we're gonna end up with the top area, which is gonna be the 22 divided by 74 squared, and square root times the 3.5 times 3.5 times 0.25. This is gonna give us 6.58 centimeter square. If from this area we can simply find the diameter of the down sprue at the bottom, which is going to be 4 over pi times the AB under the square root. This is going to give us the 4 times over shift pi, over shift pi. The square root of that is going to give us the 2.89 centimeter, which is going to be like 28.9 millimeter, right? This is gonna be the diameter at the bottom, and the diameter at the top was already given by 35. To make sure that your calculator is correct, definitely the diameter of the down sprue at the bottom, it should be lower or smaller than the diameter of the down sprue at the top. At the top it was 35 millimeter, at the bottom we got it by the 28.9 millimeter. It means that we are in a good shape, and this result makes sense. And this was what was required for this problem, is just to calculate the diameter. It was required to calculate the diameter of the down sprue, what should be the diameter at the bottom of the sprue, to avoid aspiration. And what does mean aspiration? Your objective is just to explain here what does mean aspiration by representing the two cases, like the case that you have a straight down sprue or a taper down sprue, and say the problem of the straight down sprue, explain it graphically and explain that respiration is to avoid the breathing air to fill into the mold cavity. And this is one of the serious problem that would result in some defects in the casting, and in many of the cases the casting will be rejected upon the if there is breathing of the air to fill into the mold cavity because of the porosity that is going to show up inside the mold cavity, making it weak. So that's it for this video and today's lecture. We explained, we initially discussed the different formulas and the equations, load that would be used for the riser design, for the down sprue design, in addition to the calculation of the Buoyancy force. Then I solved with you some examples and problems on these topics. By this is going to be the end of the metal casting part. We have discussed lots of things over 3 weeks, over 3 weeks we already discussed the metal casting. We discussed the sand mold design, we discussed the riser design, the down sprue design, the calculation of the Buoyancy force. This is in terms of the problems. In addition, we discussed the getting system, the shape of the mold, what does it mean mold, the flask, the sand. Even we discussed the different types of sand. I didn't explain them to you, but anyway, they are included, were included as a reading assignment to you through this course. In addition to the other concepts of the gearing system, the function of the gearing elements, the functions of the riser, all of these aspects of the metal casting in general, then we focused on the sand mold design. Starting from the next meeting, we're gonna move to the metal forming. This is a second group of manufacturing processes, but this is for the the metal casting processing. All right, so thank you and see you in the next video.